Hello everyone, we're Team 6. Our team consists of Ahmed, Fahim, Mohammed, Zaib and Alec. And we're working on the analysis and redesign of a clothing iron, and this is our final presentation. A clothing iron utilizes electricity to heat a metal heating element which removes wrinkles and creases. Our primary customer are the domestic household. Our secondary customer are clothing manufacturers and tailors who will be provided with the gravity-fed dry steam iron. Our production volume is 700,000, which is 5% of the current market. This is our assembly CAD drawing. It shows all the parts in their assembled position. We have 18 unique components in this iron. Each part has a quantity of 1 except for push buttons. Here is our first diagram. We have one main functive branch that relates to removing wrinkles. This task function is performed by the basic function of pressing clothes by adding heat and evenly distributing weight. Second basic function is to allow transition and rotation. The other functions are to prevent burns, prevent water leaks, and indicate overheating and provide steam. We use this mapping matrix to consolidate parts with similar functions and do DfM and DFA to reduce cost. We will use this quad chart to find high cost parts like sole plate from here to improve and make it cheaper. Our product family has two variants. The majority of our functions are consistent to both customer groups. We differentiate our product by the process of supplying and regulating the water. We changed 4 parts for the secondary variant. There is no need for a water lead as water is supplied from outside in the secondary variant. The plunger and push buttons are replaced with a solenoid valve to accurately send the water. The top handle is changed to fill in any unnecessary cavity. All the connection points are kept the same from primary version. This is our original assembly plan, which has unnecessary variety. We update the assembly plan so that the differentiation happens later.
From our plot chart, the sole plate and top handle have the highest cost, and they have a high functional importance. The sole plate is our platform part, and the top handle is a module part. So, we selected these two parts for manual DFA. Our total manual assembly time for the whole assembly was 253 seconds, 0.85, with efficiency of 22.45%. We consolidated the plunger lid and the top handle to make it one part. We also made an additional cylindrical extrusion to easily insert the water lid. We then switched to a snap fit for the top handle and reduced fastener count and assembly time. For the sole plate, we added fillets for easy insertion to the heating housing, reduced fastener count by doing a press fit, and attached a rotating feature to improve assembly time. This shows added fillets on the sole plate for easy insertion on heating housing. After DFA, we consolidated one part and removed 2 fasteners, which reduced our assembly time by 22 seconds. There is no impact on product function, but there is a slight mass increase for the top handle and sole plate in terms of manufacturing.
For automated assembly part selection, we selected the steam rod stand and wheel as all 3 parts share the same function of controlling steam while having a high cost. This is our exploded view before redesigning. All the handling and insertion codes are given. This is our exploded view after redesign with handling and insertion codes on the right. The bold text shows changes for insertion and handling. This is showing all the features we changed. We added a slot to enable Z assembly and minimize turning. To make the steam stand symmetric, we mimicked tall extrusion on the left. We also added a step on the tall extrusion to avoid holding the steam rod while inserting the steam wheel, and we added an external lip to avoid overlapping. This chart shows our modified features. We saved $1.14 by doing DFA on this subassembly. The product function may slightly decrease for the steam rod as it may slip out of position if the product is shaken too much. For steam wheel, there's a slight decrease in material. Additional setup on steam stand manufacturing is required because of the undercut.
The steam stand and steam wheel are both selected for process selection. They have the same function, which is steam control. Here we have the drawing for the steam stand, which is used to hold the steam rod and steam wheel in place. The center hole and the 2 slots are both critical because they help the steam stand align the steam rod with the water reservoir. All dimensions related to these critical features are given tire tolerances of 0.1 millimeters instead of 0.2. We decided the steam stand would be made out of 6061 aluminum. After evaluating all processes compatible with aluminum based on shape, mass, section thickness, tolerance, surface roughness, and economic batch size, we determined that the steam stand would have to be made by machining. Here we have the drawing for the steam wheel, which controls the steam flow. The side face slot is critical because it guides the steam rod up and down. The side extrusions are critical because they align the part correctly in the assembly. All dimensions related to these critical features are given tighter tolerances of 0.1 millimeters instead of 0.2. We decided that the steam wheel would be made out of thermoplastic. After evaluating all processes compatible with thermoplastic based on shape, mass, section thickness, tolerance, surface roughness, and economic batch size, we determined that the steam wheel would have to be made through either machining or injection molding. We therefore decided to use injection molding.
Now we look at DfM for steam wheel. We are injection molding this part. Our analysis before redesign gives us a total cost of 86 cents. DfM Pro suggests changing draft angle, having uniform wall thickness, and mold wall thickness. Key dimensions for the redesigned steam wheel are shown here. We minimized the wall thickness and therefore removed material. We made the uniform wall thickness throughout and added a 5-degree draft angle for easier mold release. We also blended all sharp corners. This is our analytical calculation after DfM. We saved 65 cents per part. The assembly cost does not change. Product function may have impacted due to draft angle on the side extrusion. Now we move on to DfM for steam stand. We are CNC machining this part. This is our analysis for before redesign. The total cost is $3.07. DfM Pro suggests not having narrow pocket regions and sharp corners. This shows key dimensions for a redesigned steam stand. These are our DfM rules implied on the redesigned steam stand. We closed off the undercut as it did not have functional importance. To avoid long corner and interference, we removed the extrusion from around the slots. To avoid thin section in the lip, we thickened it to 1 millimeter. We also blended the sharp corners for less stress concentration. This is our DfM analysis after redesign. This had 1 less setup and 4 less tool changes. The cost reduced to $2.53. This is our extrapolation curve from hubs.com. The codes are underestimating the numbers by a lot because of our high production volume of 700,000. By comparing the results, the hubs with 20% profit shows that 33% decrease in cost, whereas the analytical method has the 17% cost reduction. The extrapolation from hubs is not accurate enough for our case as it is extrapolating too far. The product function and assembly costs are not affected by any of the design changes.
We decided to include a support plan with our product to provide benefits to the customer and to the environment. Our support plan includes a warranty, giving our customers access to maintenance services and replacement parts. Parts will be reused and recycled as deemed appropriate. Additional benefits include quick repair turnarounds, customer support hotline, and cross-shipping. Our product support system not only improves customer satisfaction, but also benefits the environment through increased product lifespan and reduced waste. This summarizes our DfM and DFA analysis on a clothing iron. We saved 22 seconds by doing manual DFA. Our automated DFA saved us $1.14 for that subassembly. For the steam stand, we reduced the cost by 17% via DfM, and for the steam wheel, we reduced the cost by 75%. Overall, we saved $2.33 per iron, which saved us a total of $1.63 million for 700,000 units. This is a really good design, as most of our design changes did not abruptly affect the product functions. If we get to restart our project again, we would like to explore alternative parts for DFA and DfM analysis. Doing them on high-cost parts like the sole plate may prove beneficial. So that concludes our Team 6 final presentation. Thank you for listening.